Okay, so we'll jump right in then, if there are no questions, anything like that. So I'm going to try to tell a story. I can't say that I'm the best storyteller ever. So this is the big data story. Everybody's heard this phrase, big data, before. So Sally is a metaphorical character that discovers she can collect a lot of data very cheaply. Right? This is kind of what we're experiencing these days. We're experiencing the ability to collect data cheaply. And because we can collect data so cheaply, we collect a lot of data, a lot. Right? We do this actually ourselves on a personal level. And after a data collection exercise that may last some years, for example, 5 years, and costs some money, it could even cost millions of pounds for some scientists or some companies, we eventually make a transition from data collection to trying to derive useful knowledge and information from the data we collected. So it's kind of a learning process. So in this case, Sally eventually wants to derive knowledge and extract insight from her data. And this is a learning process. This is actually the first stage of the learning process. She discovers what a challenge it is due to the size and the complexity of the data. So data has a kind of size and a complexity, and it reaches a special threshold. And as soon as that magic threshold is reached, it becomes very difficult to extract useful knowledge and information from the data. A very, very trivial example is just, has anybody here ever lost a file before? It's a very trivial example, but it's happened to everybody here. Maybe you lost a photo, you had, you have a collection of 10,000 selfies and you want that perfect selfie, but you can't find it anymore. So a special gap appears between our ability to collect data and our ability to extract useful knowledge and information from the data. And that discovery of that gap, wow, I'm a lot better at collecting data than I am at extracting useful information. Suddenly, that's a skill. That's a skill. That's what we're studying here. And it's the discovery of this missing skill that's the first stage of learning. It's going from unconscious incompetence to conscious incompetence. Has anybody ever heard of that before? The first stage of learning. It's kind of a fun thing. Okay, I just want to check for something before I go further. So this is what that process looks like, if you want to see what it looks like, because we're very visual in this module. We like to see the things. This is a pattern of knowledge evolution. This is the pattern of knowledge evolution that is taking place with us here at Swansea University, but everywhere we have computing. Wherever computing exists, this knowledge evolution is taking place. It starts with a real-world challenge. For example, maybe we want to observe something new. Maybe we want to build something. Maybe we want to reach a new level of understanding. Maybe we're trying to answer a very special question or test a special hypothesis. That's stage one. And everybody's familiar with that. We all have questions we're trying to answer, goals we're trying to reach, things we want to build, challenges we're facing, right? Everybody knows this. For all these challenges, there's usually some physical, or we also call it analog approach. So if we want to make people healthy, we build hospitals. Right? That's a good way to help people get healthy. Or we invent new medicines or new vaccines. If we want to get from point A to point B, we build things like cars and ships and planes and those sorts of things. With the car example, if I asked you to build a car, what would be the problem there? If I picked on one of you and said, please build a car, what would be the problem? What's your name?
Anthony.
Tony.
Yeah. Budget.
Exactly. It's very difficult for one of us to build a car for two reasons. Money, it would cost a lot of money, and secondly, it would cost a lot of time. We might be dead before we successfully build a car. So sometimes we have a real-world challenge, which is to get from A to B, and as an example, we need a car, but we can't build our own car. It's too expensive or too costly in terms of time. In other words, it's not feasible. So that's the third stage of this knowledge evolution pipeline. And this is all stuff that you already know already. I'm reading your minds now. I already know what's in your minds. I know this pattern is already there. But if I asked Tony to build a digital car, that is something he could probably do after he takes a few classes. So this dashed line represents the transition from the real world or the physical world, in which the solution to many of our challenges and problems are not feasible or even impossible, to the digital world, which is on the other side of the dashed line. So I could ask Tony, Tony, I know that there's software where you can build cars with. Yeah, because cars are built in software before they're built in hardware. That's the way it works. And lots of things are built in software now. And everybody thinks, oh, there must be an app that can solve that problem for me. Like Uber. Uber can get me from point A to point B, maybe, if I need a car. And we all know that. We're still on this path that we all know. We all know about real-world challenges. We all know about physical solutions. We all know about some solutions not being feasible. We all know there's an app or some digital solution for all of our problems. This is something we already know. But where it starts to get unfamiliar is the next stage. Those digital solutions to our problems have a special characteristic. And the special characteristic is that they generate lots of data. Lots and lots of data. And I call this data chaos. They result in a new problem called data chaos, which is generating very large, complicated, difficult to understand data. And this is where we are in our education, our collective education. We kind of understand that this problem exists, even from our own personal experience. Some of you may have been in the real world at jobs and seen it at jobs, but you certainly have experienced it on a personal level already. And this module is all about trying to understand data chaos through visualization. So visualization is the tool, you could say, that facilitates the understanding and unravels the data chaos, solves the data chaos problem. And this is why we're here today. And this is happening everywhere. These are just some examples of this pattern in very familiar places like computational fluid dynamics. Anybody ever heard of computational fluid dynamics? Anybody ever heard of engineering? There's a big engineering college over in the few buildings over. They're very familiar. They're generating massive amounts of data and they struggle to understand it. Physicists and astronomers generate massive amounts of data through experiments and satellite imagery and telescopes, but they struggle massively to manage it. Marine biologists and biochemists, with all their measuring devices, are generating massive amounts of data, and they're struggling to understand it, desperate for visualization solutions. Sports scientists like the Super Bowl, right? You don't usually think of sports in terms of a data-centric view, but they are very data-centric events, so they can be very data-centric events. And what do? They archive videos of the games, and then they play the games, they rewind them, they play them again, rewind them, play them again, and try to look for patterns. There's also text data, so every library, you don't usually think of a library as a data set, but that's what it is. You're going in there to find special data, and you're trying to find, like, wow, that's good. That's a good example of data chaos, going into the library and trying to find the data that you want. And it's such a fun challenge that you can get a degree just in library science, how to organize a library. Governments and councils are collecting your data, right, to try to understand the behavior of their local population and allocate resources in the most efficient ways. Now, on the left side are kind of examples that are associated with professions, different professions. On the right side are examples that are associated with individual people like you. Data that's associated with you. Banks collect a lot of data, right? You look at your bank statement and you have lots of transactions and you're trying to figure out, where did all the money go? It's gone. And call centers, every time you call somebody or you call anywhere, that data is stored somewhere by telephone companies, for example. There's retail data. Every time you go shopping, whatever you buy is stored in a database. You know, the purchase price, the wholesale price, where you bought it, what time you bought it, all that sort of thing. Every time you visit a website, that data is recorded. Who visited the website? Where were they? What kind of device were they using? And so on. Transportation, every time you go somewhere, that data is recorded. Every time you get on a plane and so on. Every time you visit an NHS practice, your healthcare data is recorded. And you collect your own data. You collect photos, for example, files and videos. So you collect data even if you don't think of it that way. You're collecting lots of data. So this is something that's happening everywhere to everybody all the time. This is a ubiquitous challenge. Like, you can't escape it if you're using any computing devices. And I think it's one of the reasons is because people just like to collect. I think it's just human nature. Like, it's nice to collect things. I think it's like related to survival or something. the more we collect, the better our chances of survival. Like, it's a leftover artifact of the days when we were trying to survive. And yeah, that's at least my theory. Any questions so far? Is the attendance register being passed around? Where is it? Okay, good. It's a little warm in here, isn't it? I see that the windows don't open. Do you think it's worth opening a door?
Yeah.
Might be. Might be. Should I? This is just a little diagram of the visual cortex. This is something we don't usually think about, is our 5 or 6 senses and how they're related to our brains and our brain processing. But we have this visual processing system that we're born with, usually called the visual cortex, and it's our most powerful sense. So several billion neurons are devoted to analyzing visual information. So that's roughly 30% of the cortex. Now that number sounds kind of interesting, but it's even more interesting if you compare it with the other senses. So that's compared to 8% of our cortex dedicated to touch, or 3% for hearing. So our visual system, our visual cortex is very predominant. It's much bigger than the cortex allocated for the other senses. So we may as well exploit it. If so much of our brain is dedicated to our vision system, and I think we know that intuitively, we may as well take advantage of it. Now, the visualization itself is very old. The concept of visualization is very old, especially if you consider things like drawings as visualizations, which they are. This is a drawing by Leonardo da Vinci. Anybody happen to know what that is? Can anybody recognize that? That is a flow visualization. So flow going in one side of a square cylinder and coming out the other, and him drawing the pattern of flow. So that's a very old example. So like cave drawings are arguably a data visualization. So it's an intuitive step to make something clearer. You're all familiar with things like pie charts and line charts and bar charts. Those are very, very exciting examples of data visualization. What we're really talking about in this module is more advanced and computer-centric visualization with an interactive element to it. That's really what we're talking about in this module. So not hand-drawn things, not things that are manually done, but software that automates the visualization or semi-automates the visualization that we can interact with. So we can change parameters and watch what happens to the resulting imagery. It's its own scientific discipline since 1987. So if I think correctly, is that 30 years ago? So it's about 30 years old now, a little bit more, which is kind of new when it's compared to some other disciplines. The classical, for example, artificial intelligence is so hyped right now, but artificial intelligence is much older than data visualization. So data visualization is on the newer side of the topics. The first conference took place in 1990. One of the first books was published in 1997, so that's only 20-ish years ago. Here are examples of what we're kind of thinking about in this module. Some medical visualization examples. Right, this is an image of somebody's skin. This is an image of somebody's bone surface. Here are some more examples of what we're going to be looking at in this module. These are, anybody recognize what those things are? Any automobile, like, I think they're called gearheads in the class. Any gearheads? The days of gearheads seems to be gone. When I was a kid, like, there were lots of gearheads around. Like, people were excited to open up the hoods of their cars and look inside and try to figure out how it worked. But these are some flow visualization examples. This is an automobile component. This is the combustion chamber of a gas engine. These are intake ports and outtake ports. We're also going to study information visualization, which is generating very abstract imagery from abstract data. Data that's not associated with any special spatial coordinate or temporal coordinate. So what is visualization good for? Its strengths. But before I jump into that, I forgot to say, give a kind of definition of data visualization for the purposes of this module. A definition I like to use relates to computer graphics. So some of you might, if I asked you, like, how would you define data visualization? Like, what is it? Some of you might have an association with computer graphics. Is the attendance register going around somewhere? Okay, are people signing it still and passing it around? Okay. So when you think of computer graphics, what do you associate computer graphics with? Anybody have thought on that? What do you associate computer graphics with? I think you took a computer graphics class. Didn't you all take a computer graphics class? Anybody have any associations? I guess everybody's too scared to video games, exactly. What's your name? Sam. Well done, Sam. Yes. Games. A perfect application for graphics. Any other applications besides games? There's one other kind of popular one, let's say. Has anybody seen Aquaman? Who's seen Aquaman? Were you happy with Aquaman?
It didn't really leave a lasting impression.
So games and movies. You associate well, at least a lot of people like myself associate graphics with games and movies. And games and movies are also usually fictional. So they're fantasy or fictional, usually. Not always, but. And data visualization is really using computer graphics, but to convey nonfiction, to try to convey something real. That's the way I think of data visualization. So using computer graphics not to depict fantasy like in games or Aquaman, but to depict something real, something that actually exists. Those images that we saw are trying to convey imagery of things that really exist, right, to some degree, to some, with some uncertainty, obviously, but that's the idea. And visualization is good for exploration. This is the case when you have a data set, like in assignment 1, which we're going to talk about later, and you don't know anything about the data set. You've never seen it before. You didn't create it. You've never worked with it. You don't know what it looks like. So you can use data visualization to explore data. It's good for analysis. This is the case when you are already very familiar with the data set. Maybe you helped generate it. Maybe you were part of the team that generated it. Maybe you collected it on purpose with a special aim to confirm or refute a hypothesis or to answer a question. Then you need to analyze the data. It's also very good for presentations. That's what people usually associate with data viz presentations. After you've done some exploration or after you've done some analysis, you present and communicate the results to a greater audience, and that is presentation. There are also 2 other more subtle but very important aspects that our data visualization can help with. And one is acceleration. So if we have a very large, complicated data set, what do we do with it? Anybody have any ideas about that? If I give you a very large, complicated data set, what do you do with it? Fundamentally, with all of your data, what do you do with your collection of 10,000 selfies?
Try and that it is a simpler, smaller set of data.
Yep, that's one thing you do with it. What were you going to say?
I was going to say just remove redundant data.
Remove redundancies. It can also be boiled down to something very simple, which is search. That's essentially what you do with data, isn't it? You search. Everything is kind of a search process. You go into a library, you start searching. You go on the web, you start with Google. It's a search. Like, kind of everything is a search process, isn't it? You go into the shopping mall, and you start searching for your favorite clothes. So it's all about searching. So data visualization accelerates the search process. It makes a search process, it takes an existing search process, or maybe a non-existing search process, and makes it very fast. It can make it extremely fast. Like if I gave you a spreadsheet with 1 million numbers in it, and I said, please tell me how many times prime numbers appear in the spreadsheet. If you were to try to do that manually, it could take, you might never finish. You might never finish your search for prime numbers. But if you use data visualization, you can find the prime numbers in a few seconds. Right? Just a list of prime numbers. So it can accelerate a search process. And sometimes it enables a search process that's impossible otherwise, like it can't be performed without visualization. It's also good for validation. In other words, a lot of people collect data, explore data, and analyze data without visualization, and they think what they're doing is right. They're pretty sure. They're kind of confident that what they're doing is correct, but not 100% confident. As soon as you start generating images of that data, it validates, it confirms or refutes that what you're doing is actually correct. And this happens a lot. As soon as you start to see the data, you find out, there's an error. Or, oh yes, it's behaving, the result image is what I expected it to be. So it's a kind of validation. This module has 3 sub-directions and topics: volume visualization, flow visualization, information visualization. It's a little bit schizophrenic in that sense, like multiple personality disorder. Usually data viz modules don't have these 3 topics, but since I'm schizophrenic, then all the things that I teach are also schizophrenic. Volume visualization is concerned with data that's arranged in 3D space, right? A volumetric space, and a very typical example is medical visualization. Flow visualization is also usually associated with, it's definitely associated with space, like 2D space or 3D space. But it's different from volume visualization in that flow visualization studies the movement of fluid, typically. So the patterns of motion that fluid takes. And those both belong to a discipline called scientific visualization, and they have an inherent geometry. In other words, all the data is associated with time and space. A special time and a special spatial position. Getting back to the search example, when you get an X-ray, that's an example of a volume visualization, and the doctor is searching for abnormalities. Anything that doesn't look right, that looks broken. And every data sample in that X-ray has a very specific position. It's like in the right position or the wrong position, kind of. So that means it has an inherent geometry. That's what this inherent geometry means. Information visualization means the data has no inherent geometry. It's abstract. For example, usually data that's found in a database is abstract. A list of telephone numbers, a list of credit card transactions, those types of things. A collection of photos, perhaps. There's no inherent geometry. The exact location of the data is abstract. There's no XY coordinate associated with the data. Any questions so far? The attendance register is still getting passed around. Over there, I guess. Okay. Suspense is agonizing, isn't it? The attendance register. Question?
Is virtual reality ever used in data visualization?
Yes. Sometimes virtual reality and data visualization are combined. And if you're really interested in that, there's a 90-minute video on the DataViz YouTube channel on exactly that topic. It's called When Data Visualization Met Virtual Reality. And you can find but virtual reality is creating a synthetic reality, right? You have some reality that's it's synthetic. It's generated by software. That's virtual reality. It's replacing the real world with a virtual world. But you can change that. You can add things to your virtual world that could be real. You could add data visualization to a virtual world. You could add some things to virtual reality that changes it. You can mix virtual and real worlds, right? And that's mixed reality. So yeah, I recommend having a look at that 90-minute talk just on that exact question. Any other questions before we go to the next topic? Viz pipeline. What's your name?
Greg.
Greg.
For the coursework,
Yep.
is that in Java or Python or like
Very good question, because I think everybody's wondering that, but nobody's asked it yet. The first coursework does not involve any programming, so you don't have to worry about that. The second coursework is in whatever language you like. So, yeah, could be Java, could be C++, could be C, Python, whatever you like. And the third coursework is more on the theoretical side. Any other questions? Your name?
Ziggy.
Ziggy.
Yeah. So this is for the third course on Blackboard. It says optional here in brackets.
Yep.
Does that mean it's like the top 2 coursework you've done is selected or something like that?
That's right. The third coursework is optional. And that means if you get a score that is below what you are happy with or satisfied with on 1 and 2, assignments 1 and 2, you then have the option of doing assignment 3 to try to raise your coursework average. That's the way it works.
The highest 2 out of 3 count then.
The first 2 assignments always count, so to speak, are always included in your average. If you leave out the third one, the first 2 are averaged together, and that's your assignment 3 score. So your average stays the same. Does that make sense?
Yeah.
Good, very good. I can see that the level of anticipation is very high. I like it. So the last bit of today is the visualization pipeline, which is, we kind of already saw a pipeline-ish in this lecture, which is that pattern of knowledge evolution. That's kind of, it's sort of like a pipeline. It's the stages of learning in some ways. This is a data visualization pipeline, but it is, we might not finish it. We'll just look at it briefly. We might not finish it right now. But this is typically the process we go through to create a data visualization, an image that we want to see of data. There's an acquisition phase that we're usually not involved in. Somebody generates the data, and that's usually not us. It's usually somebody else. The rest of the world is generating data. Everybody else. And then they're begging us to help them understand it. That's really how it works in the data viz business, so to speak, if you get interested in the subject. If you get to be knowledgeable in this subject, your marketability skyrockets because you become a very desired commodity. This is a very desirable set of skills to have, which means your job opportunities are very high in this subject. That's because everybody's generating lots of data, and they're desperate for people that can help them understand it. And they know that data visualization is a key skill for this understanding. And so people that end up specializing in data viz are extremely valuable and extremely marketable and can essentially work wherever they want. different countries, pretty much anywhere. Sort of like nurses. So there's an acquisition phase, then there's an enhancement phase. It's usually some changes are made to your original data sets. Maybe some errors are corrected, maybe some holes are plugged, maybe some filtering or smoothing is performed. That's called enhancement. So some changes that are made. Maybe the format is changed. That's assignment 1, by the way, and assignment 2. Then we take that enhanced version of the data and we start mapping it to shapes. Things like points, colors, lines, edges, triangles, squares, cubes, tetrahedra, textures, things that we can see. That's really what the focus of this module is. It's on this phase of the Viz pipeline. The last phase is taking those geometric primitives and then rendering them. That's computer graphics. So how do you render 1,000 or 1,000,000 or 10 million pixels, for example? That's something you already know from your computer graphics class, right? I'm sure you remember everything from your computer graphics module. You don't panic. Like any critical information you need from your computer graphics, we'll review here. Okay, I guess we will stop there. Any questions? Did the attendance register make it all the way around? Everybody? I'll see you all at 1700 hours.